Hello, I'm Charlie Bryant, and this is Lab 4 on Oscillation. Our objectives are to compare the observational data and computational model of two-dimensional spring motion, and then we're going to visualize the energy changes and determine if the energy principle is satisfied. So the physics principles involved are Newton's second law, which tells us that the change in velocity is equal to the net force times the mass over the change in time, and the energy principle, which says that the change in energy is equal to the work done on the system plus the heat added. If there's no heat added or work done, then the change in the energy will be simply zero. So we took some simple motion data and then made a plot of x position versus time and y position versus time in software called Tracker. Then we wanted to make a computational model to compare it to that positional data. So first of all, we inputted our initial conditions, which were the mass of the object, its initial position, which we just found from the Tracker software. Its initial velocity was 0, it started from rest, and we're going to start our time from 0. Next up, we need to do some calculations for the rest of our initial conditions. We know that t, the period of the spring, is equal to 2 pi times the mass of our object times k, which is the spring constant. So then solving algebraically for k, we find that k is equal to 4 pi squared times the mass of the object divided by t squared, the period. So to find the period, I simply looked at our data and I measured the distance between two troughs, which will give us the period, one period of oscillation, which I found to be 1.488 seconds. So then plugging all those values in, we find that our K is 7.17 newtons per meter. Now that we know K, we can solve for the initial relaxed length of the spring. Because the spring is at static equilibrium when it's at rest, we say the net force is 0, so the force of gravity plus the force of the spring is equal to 0. So in that case, their magnitudes are the same. So mg, the force of gravity, is equal to ks, which from Hooke's law tells us the force of the spring is k, the spring constant, which we just found, times s, which is the stretch. The stretch is equal to the length that the spring is stretched to minus its relaxed length. So once again, solving algebraically for its relaxed length, we plug in all of our values. Our initial value for L is 0 0.7 meters, which we know from the video. And we find that our relaxed length is 0.151 meters. So then we plug all those into Tracker. So continuing on. This is where the implementation of Newton's law lies in the code. We have our force of gravity, which is negative g times our ball's mass in the y direction. The force of the spring, which is the application of Hooke's law, and notice its direction is in the L hat direction, which from the code above is in the direction that the spring is pulling the object back towards the origin. So our net force is simply the sum of those two forces acting on it. And then here's the application of Newton's second law, which updates the velocity, which then in turn updates the position. Here's a graph of the predicted versus observed motion. Now, it's a very accurate model, but there's discrepancies due to drag force in the form of air resistance and a round-off loss due to the various software we used. So what does it mean? Now I'll move on to that section. We're going to compare the periods of x and y motion. The x period is 1.615 seconds, and the y period is slightly less at 1.48 seconds. So here in Tracker tables of the x position versus time, y position versus time, and notice how their periods are not quite the same. Now, why is that? It's because we're actually looking at two different systems of periodic motion. The x is a pendulum, and the y is a spring. So different forces are acting, and so therefore the periods won't be the same. So is the energy principle satisfied? Well, let's take our system as the mass of the object plus this and the spring and the earth, and there's no work done on the system. We're going to go ahead and assume there's no heat added, so therefore our change in energy will be 0. The components of that energy are the kinetic energy of the object plus the potential energy due to gravity and the potential energy of the spring. So now let's go back to our model and see if that does in turn equal 0. So kinetic energy is 1/2 mv squared. Potential energy due to gravity is mass times acceleration due to gravity times the height. And the potential energy from a spring is 1/2 times the spring constant times the stretch squared. So I simply inputted that into the code. And then what I did was I plotted how they changed over time. So in our time step that we used the first graph, we found the position. This is a plot of the change in energies, with red being of the potential energy of the spring, green being potential limit of gravity, blue being the change in kinetic energy, and then this yellow, the total change in energy, is the sum of all of the above values. So that's the thing that we need to pay attention to. And notice how this yellow line flatlines right at 0. So therefore, that tells us, our model says that the change in energy at any point in time is 0. So therefore, yes, the energy principle is satisfied. And thanks for watching.